Hello and welcome to my series on advanced classical mechanics, aimed at students who are currently or may be starting a degree in physics. These series of lectures will really dive deep into the heart of classical physics, where we'll look at many concepts including Lagrange dynamics, time translation invariance, symmetry, Poisson brackets, and so much more. So again, this is aimed at students who are wishing to take a physics degree. However, A-level students are also welcome to give it a go. Why not? So the requirements. You should be confident or at least familiar with all topics listed below. This will allow you to gain full understanding. So for physics, you need to know Newton's equations and concepts, basic laws of physics, for example, the conservation of energy and momentum, electromagnetism, projectile motion, and vectors. Alright? So my A-level physics series will also be very useful for you to recap and learn the basic physics concepts. And I strongly recommend that your A-level physics knowledge and mathematics A-level knowledge is at a high standard before you proceed with these lectures. And for your maths, you need to know calculus, including multivariable calculus, trigonometry and geometry, and algebra. Right. So here's a list of the lectures in order. So lecture 1, the nature of classical mechanics. So here we'll be laying a foundation for classical physics, which will basically be on deterministic laws, reversible laws, conservation of information, and so forth. Now we have interludes here. So these interludes will basically cover the material that I mentioned in the criteria for you to understand these lectures in detail. Okay? So for instance, in interlude 1, we're going to look at over spaces, trigonometry and vectors. Interlude 2, we look at integral calculus, and interlude 3, we look at partial differentiation. So yes, lecture 1 is on the nature of classical mechanics, lecture 2 is on motion, lecture 3 is on dynamics, lecture 4 is on systems of more than one particle, lecture 5 is on energy, lecture 6 is on the principle of stationary action, lecture 7 is on symmetries and conservation laws, lecture 8 is on Hamiltonian mechanics and time translation invariance, lecture 9 is on the phase-space fluid and the Gibbs-Liouville theorem, lecture 10 is on Poisson brackets, angular momentum and symmetries, lecture 1 is on electric and magnetic forces, and finally, lecture 12 is on central forces and planetary orbits. Now, lecture 12 will act as additional information that will secure your knowledge further. Okay? So it's not compulsory to the series, but it's always good to have that extra knowledge. And a very quick note, all of these lectures will be split into parts, each being a video of a maximum duration of 15 minutes. Alright? So, without further ado, let me give you a brief introduction on what classical physics is all about. The term classical physics refers to physics before the advent of quantum mechanics. Classical physics includes Newton's equations for the motion of particles, Maxwell's equations, and Einstein's general theory of relativity. But it is more than just theories of specific phenomena. It is a set of principles and rules that govern all phenomena for which quantum uncertainty is not relevant. So those general rules are called classical mechanics. In general, the job of classical physics is to predict the future. In classical physics, if you know everything about a system at some instant of time, and you also know the equations that govern how the system changes, then you can predict the future. That's what we mean when we say the classical laws of physics are deterministic. If we can say the same thing but with the past and future reversed, then the same equations tell you everything about the past. Such a system is called reversible. So remember these keywords, determinism and reversibility, as they will prove to be very vital to lay a basic foundation of classical mechanics, which I'll establish in Lecture 1 in the next video. See you then.